Okay, the exciting conclusion of lesson 2.4. So this is the second part here. So we're still in this idea of working with these polynomials and their zeros. So I wanted to show you something first to start this one out. This one talks about another way that you can sort of narrow down your possible answers so that when you go to do your synthetic division process, you don't have quite as many numbers to choose from. However, this is really only beneficial if you're not using a graphing calculator. Because if you are, obviously we're identifying real zeros based on looking at the graph. But if I didn't have a graphing calculator to look at, here's the theorem. So I'll take you to page 197 real quick. And it looks like this. You can read for your pure enjoyment, but let me see if I can simplify this a little bit for you. So when you do your synthetic division, you know the number that you put in the box is this k value. Okay, so that's what this represents. So if my factor is x minus k, then we put positive k in the box. And if your k is positive, when you do your synthetic division, if every number on the bottom line is either positive or 0, then that means this number that you had in the box represents an upper boundary for the zeros of the graph. So if you look at this one right here, that's what this D would represent. Okay, and so this is a positive number. If I did synthetic division and all the bottom numbers in the bottom row, the results were all 0 or positive, that makes D an upper bound, which means all of my real zeros are below this number. And then the opposite of that, so what if your k value is negative? So if I put a negative number in the box and do my synthetic division, and this is where the rule gets really fun, if all the numbers in the last line are alternating non-negative and non-positive, and you know they say non-negative because this and then would include 0. So when they say non-negative, this means 0 or positive, and those alternate with values that are either 0 or negative, then that would make k your lower boundary. And so I'm going to show you one of those because that's kind of there's a lot going on there. So anyway, so the C represented the lower boundary, D represented the upper boundary, and if we had these scenarios that they described, that would tell me that all of my real zeros are somewhere between those two values. But again, only really beneficial if you didn't have a calculator and you were trying to narrow down your list of possible real zeros. But I'll show you how this would kind of play out in a problem. So if you're looking at this one, here was the polynomial function, and they were testing in the box positive 5, and then they tested negative 5. So here's what you got to notice. When they did positive 5, so this is a positive k value, you'll notice all of the numbers, 2, 9, 38, these all came out to be positive numbers. So, and the rule was, if these are all positive or 0, then this represents an upper boundary, right? So I know at this point that all of the zeros of this graph are less than 5. If I did it with negative 5, and my signs alternate between positive and negatives, or 0, you can have 0 in there, but if they alternate, then the negative represents the lower boundary. So this would tell us, based on this information, that all of my real zeros are somewhere between 5 and negative 5. So I guess that helps narrow things down a little bit, but you'll see here in a second why that didn't do a ton for us, but I want you to see how all this would play out. So let's just say this is the same function, same polynomial function that we were just talking about. What if they said, here you go, find all the real zeros? And so they just give us that, and we got to go through our big old process of finding real zeros. So one of the first things that we looked at in part 1 of this lesson was, remember the whole P over Q? So if I did all of my factors of 3 divided by all of my factors of 2, positive or negative, that would give me a list of all of my potential rational zeros. Looks like this. Here's my list. Well, if you notice, these are all the numbers that we talked about that we said, okay, then these are the numbers we would try putting in the box to see if we could find the zeros, right? Well, if you notice, all of those numbers are already between positive and negative 5. So the whole idea of those being upper and lower boundaries didn't help really narrow down our list. So most likely the way that would play out is, what if I said, I want you to try +1, right? So you tried +1 and you came out with, I know this isn't the case, I'm giving you sort of a made-up scenario, but if you had all positives in the bottom line, and so therefore +1 represented an upper boundary, well, then I guess that would kind of help, because then 3/2 and +3 could both be taken off the list, right? If I figured out that +1 was an upper boundary. So you can still keep it in mind. Maybe that would help in some cases. We can take some advantage of using a graphing calculator to help us narrow down this idea of where those zeros are going to be, so that we don't really have to do those upper and lower boundaries. So anyway, I wanted to show you something on this before we do one of our own, but don't worry, we are going to do one of our own. When they tested 1, they did find a 0, so they got a winner. Remember, this is what you're looking for. 0 remainders means that this is a 0 of that function. As a factor, this would be written as x minus 1. So we got that going. So we found a winner. We found one of our factors. So if I were to take the x's and plug them back in, so 2x to the third plus x to the second minus 6x minus 3, here's what would be left next to this factor right here. So then they said, okay, let's test one of the other items in the list. And if we were looking at a graphing calculator, you can see why they chose -1/2 as a potential winner. So they tried -1/2. Here's what they came out with. So if we look at this one, again, came out with a 0, which was a winner. So they found one of the answers. So they said, awesome, now we have another factor of x plus 1/2. Here's what's left. And so they put that into this factor. So they wanted to break this down one more time. Typically with a quadratic, it means you can break it down. This one wasn't so pretty, but I wanted you to at least see where this information came from. What they did first was factor out 2 as the greatest common factor. That's where he came from. So what would be left? You would have x squared minus 3. So this is what was left. And so what they did on this was they said, okay, let's use a difference of 2 squares to break it down to look like this. So that's what they did in kind of their final step to break it down into all their factors. Remember, some questions can just ask you, what are the factors? Or they'll just say factor. So, this would be this entire problem in complete factored form. So if that's what you were asked for, then great. If they said, what are the zeros, or find all the real zeros, then remember what we do. We take each factor that has x in it, so 2 is not one of those items, but you take each one that has an x in it, set it equal to 0, and you solve for x, and that's going to give you your list of zeros. So, but here's one of the main reasons I wanted you to see this. You guys know that this number and this number are not rational numbers. They're irrational, right? So when we did this idea, they're not in that list, right? Because this is your list of potential rational zeros. So it is quite possible to get an item on the list, like this one. I think this is our square root of 3 right there, which I think is about 1.7. So if I were to look at this, whatever this is not in this list. So that's why I said if you think you have a winner, you have to test it with synthetic division to make sure you're really seeing what you think you're seeing. And that's why we still use synthetic division even though we're using a graphing calculator. Okay. So that one ultimately said find all the real zeros. So there were 4 real zeros. 2 of them were rational, 2 of them were irrational, but they were all real. So that's why when you look at that graph, you saw that it did hit the x-axis in 4 places. Right? So that means there were 4 real zeros. So let's try one. And we're going to use our graphing calculator to help us out a little bit. So let's try 22. And we're going to plug that in. So 2x to the third plus x squared minus 15x plus 7. And let's take a look. All right, so here's what we want to keep in mind. This is x to the third. So because it's x to the third, I do know that there are 3 zeros. But remember, just because there's 3 zeros doesn't mean they're all 3 real zeros. But when I look at this graph, there's 1, there's 2, there's 3. So I can see on the graph that I do have 3 real zeros. And so these are all ones that we're going to be able to identify here. All 3 of them. So if we were to list out our possible rational zeros, factors of 7 over factors of 2, right? So you could have 7, you could have 7 over 2, or you could have 1/2, or you could have 1. Right? So those are sort of our list of possible zeros. So if you listed them out, I'll do a quick list here. So plus or minus for all of these. Could be a 1, could be a 7. If we had 1 over 1, if we had 1 over 2, and if we had 7 over 2. All right, so plus or minus for all those. So there's 8 possible rational zeros. Based on this, I definitely want to stay away from positive 1. I want to stay away from negative 1. It's clearly not either one of those. So he's out. 7 is out. 1/2. 1/2 looks like it might be a winner. So let's try positive 1/2 and see if that's a winner for us. If you look at this one, so here's an interesting one. It looks like negative 3. Right? It's real close to negative 3. But negative 3 is not on our list. Right? Which means this is probably an irrational number. So we'll take a look at that at the end of all this. But I definitely want to test positive 1/2 because of what I'm seeing right there. So let's give that a shot. So I'm going to bring down my coefficients. I got 2, 1, negative 15, 7. Always looking for gaps. I might need to fill in with a 0. So a little synthetic, we're going to bring down that 2. You guys know the process. So I'll get through it real quick here. I think we got a winner. And we do. So we got a remainder of 0. 1/2 is a winner. That is what we were seeing on the graph. I can throw my x's back into this, and I have 2x squared plus 2x minus 14. So keep something in mind. Once you hit the quadratic stage, you do not have to do synthetic division again. But that's a good thing, because I don't think either one of the remaining zeros are rational numbers. I think those are both irrational numbers. So let's check that out. So one of the things I'm going to do to solve this, first of all, set it equal to 0. So I'm just solving a quadratic. You can factor it, you can quadratic formula, whatever, complete the square. You got many methods for solving quadratics. Definitely one thing we should do is divide out the 2's. So if I just divide this entire equation by 2, make life a little easier for myself, you'll notice that this is not factorable. There are no products of negative 7 that would add to be 1. So this is not factorable, which is why those two solutions are not rational solutions. If they were rational, this would be factorable. But it's not. So my other option is quadratic formula. So one of our options, I know you guys know this one. Let me just say it as I go. Negative b plus or minus square root of b squared minus 4 times a times c over 2a, all over 2a. And a is 1. So there's my setup. Let's do a little cleanup on this. Under the radical, I am looking at 1 plus 28. So and those two answers represent those other values that we were seeing on the graph, which are not rational numbers. Obviously, square root of 29 is not rational because it's not a perfect square. So there's our 2 remaining missing zeros. So this one in particular did say find all the real zeros. There's one of them. So at the end of this, you should really sort of list out the zeros. That's one of them. this represents the other two real zeros. Let's try this one. I wanted to show you 24. I picked this one specifically because I wanted you to keep in mind synthetic division is a way of breaking down a polynomial if you can't factor it. But if you see something that you recognize as factorable, or you have a better method or a quicker method for breaking it down, go for it. So as I look at this one, this is just a trinomial, and this is factorable. What two numbers make positive 7 that add to be negative 8? So if I wanted to break that apart, I could break it apart as x squared minus 1, x squared minus 7. And if I set those equal to 0 and solve them, I'm going to come up with my 4 solutions. So if I set x squared minus 1 equal to 0 and solved it, I would get plus or minus 1. And if I set that equal to 0 and solved it, I would get plus or minus root 7. And so on this one, way quicker to just factor it. So if you recognize that, take advantage of it. Okay, and so again, that was x to the 4th. I was expecting 4 zeros. We got them. They're all 4 real. 2 are rational and 2 are irrational. And so these we could have pulled from the graph with synthetic division, but those you would have had to solve for anyway. So, yeah, let me jump over to one last thing, and this will be it. Wanted to remind you of something. This was in Algebra 2. I know you've seen this before. Probably may not remember it, but I'll keep something in mind for a second. And actually, I'm going to show you this to sort of piggyback off of. You remember, sorry, let me go down a little more, that if we had a factor of x minus 1, then that made positive 1 one of our solutions, right? Opposite signs. Your solutions, your zeros, and your factors have opposite signs. So when they say find the polynomial and they give me some zeros, well, if negative 2 is a 0, what is the factor that would have produced negative 2? Of course, that would be x plus 2. What is the factor that would produce 0? That would just have to be x. And the factor that would produce positive 1, as we just saw up above, would be x minus 1. So these are the factors that would produce those zeros. So if I can now just go through distribution and multiply all that fun stuff together, I will get my polynomial that produced those zeros. You can go in any order. I would start with those guys. So if I just multiplied the first one and the third one together, that would give me x squared plus x minus 2. And then I would multiply the x to all of that and get x to the 3rd plus x squared minus 2x. So this is the polynomial function that would produce those zeros. So that is it for 2.4.